Yeah, no, Mike, we'll get underway now. We've got quite a few people on the call, so we'll make a start. So, yeah, so just for myself, my name is Philip West. I'm the current chair of CIBSE North East, and just thanks everyone for joining the call this evening, and thank you for Mike in advance for doing the presentation. The session is being recorded, so it will be available on the CIBSE North East website if anyone wants to watch the event again. And Mike's going to share the presentation that can be sent to yourselves as well to obviously read through at your leisure after the event. And similarly, if you have attended this evening, CIBSE will be sending your CPD certificate to you after the event has finished as well, so that'll come straight to you. So just a couple of housekeeping rules for this evening. So if everyone can just keep the microphones on mute while Mike does his presentation, and if anyone's got any questions, if you could just please use the comment box just to put your questions in as we go through, and then Mike's going to spend 15-20 minutes at the end of the presentation going through the questions and hopefully answering them as best as they can. So yeah, that's great. So I'll hand it over to Mike, and yeah, thanks again for attending.
Thanks. Can you see, just before, you can see my screen, can you?
Yeah, we can see your screen, Mike. Yeah.
Right. Okay. So yeah, thanks for that, Phil. My name's Mike Willis. I'm Business Development Director for Huber Technology. We are a manufacturer of German. Sorry, I'm just trying to go to the next slide. Okay. We're a manufacturer of German wastewater primarily, treatment equipment, principally screens and sludge treatment. But we manufacture purely in stainless steel. Just south of Munich, that's a picture of our factory there. That's a 300 million euro turnover now that we do on an annual basis, with over 1,000 employees worldwide. The UK division is a wholly owned subsidiary of the German manufacturer, and we employ around about 70 people in the UK, and we do anything between 10 and 15 million pounds a year, depending on where we are in the water company 5-year cycle. In the UK, we sell roughly 150 pieces of equipment in a year. The Huber family goes back over 100 years producing equipment, and there's an old picture on the right hand side. If any of you can see that there, we still make those in one way or another. We first started supplying equipment in the UK in 1986. We supply all of the UK water and sewage companies, as well as the Scottish Water Company and Northern Ireland Water and Southern Irish Water in Southern Ireland. We've got about 160 million quid of asset base in the UK, and our core equipment includes screens, sludge screens, inlet screens, storm screens, and as yet, which we'll come on to, we haven't sold any of the heat from sewer equipment, but we'll come on to that and the reasons why we haven't sold any of that yet. But let's get on to the subject matter, which is extracting low-grade heat from wastewater. So you can see here, when municipal sewage is first generated, it has a temperature of roughly 23 degrees C. By the time it gets to the sewer, it's round about 11 to 14 degrees centigrade, and then it gradually drops off until it goes back into the receiving water at around about 10 or 12 degrees C. Industrial applications can be 60 degrees or above, and I'll give you a case study of where we're extracting heat from a hospital where they superheat all the water in order to sterilise their instruments. So there we go. So although there is a low-grade heat, there is a lot of sewage. So it's a question of extracting that low-grade heat and ramping it up, a bit like at the moment they're talking about ground source heat pumps and air source heat pumps. This is a similar sort of thing, but extracting that low-grade heat from sewage. So that's the temperature log of a typical wastewater treatment plant in Europe. It could be anywhere in Europe. It's pretty steady right the way through. I apologise for the fact.
Is that centigrade?
Yes, that will be centigrade because it's just above 10. Sorry about that. This whole, I had to turn this. This is built for Americans. So that is now in degrees centigrade. So you can see on the right scale, that's the centigrade scale. So the red line is the air temperature. So even though that drops over here at the end of the year, the water temperature of the blue line there stays pretty constant, as I say, between 11 and 14 degrees centigrade anywhere through Europe. And it's that heat that is available to extract. So this is a typical energy profile for a London building office, and where the heat is used. And you can see that actually the reason for the title of this presentation being heating and cooling is that it's as energy hungry to cool a modern building as it is to heat it up. And that is what you can see there is just the amount of energy required in order to maintain a building's temperature. So how do we extract low-grade heat from a sewer? Well, you can see here we make a sewer intervention. Hopefully you can see my cursor there, but the sewer intervention is made in the sewer, and we bleed off a proportion of the flow from the sewer. The sewage comes into a screen. I'll show you a screen in a minute, but either way, that's the screen removes all solids in 6 mil two dimensions. So it's a 6 mil perforated screen. The screenings themselves are transported up via an auger and discharged back into the sewer, where they can go back to the sewage works. And the screened sewage is pumped then into a building which contains what we call the ROWIN, which is our heat exchanger. Picture of it there, and then that low-grade heat goes into a heat pump here, which takes the water up and then goes into the building. So it will resemble in many respects a ground source heat pump or an air source heat pump in its configuration. So this is, I said I'd show you what a screen looks like. So this is an actual installation in a place called Winterthur in Switzerland. So you can see here that there's an intervention into the sewer, and it comes into the inside of the screen there, and then the sewage comes out, and this is a lifting chain for a pump that takes the pump out here. So the sewage comes in through that pipe into the screen. The sewage, the screenings are conveyed up that pipe there, which is this pipe here, and is discharged back into the sewer. And this sewage here is available for heating, and it goes up here, and that will discharge somewhere over here back into the sewer as the sewer flows away from the building. So that's the screening element. That's the pump station looking down from the top, so you can see the duty standby pumps on the right hand side here, the incoming sewage pipe coming into this unit here, into the screen. The screenings will come up here, and these pumps will take these sewage out and away into, okay, it's not the next picture, actually I'll go to the next picture, into these, which are the two heat exchangers. So this is the first element of the design that I showed you there. So these are two what we call BG8s. So these are what's actually taking that low grade heat out of the sewage and into the internal flow mechanism for the heat exchanger and away into the heat pump. As your engineers, you might be interested in this, but that's a closer look at the 6mm screen. So you can see the perforations going up the side there, and the incoming pipe here. So that's just a surge vessel up here. The sewage comes in there, goes in there, and that if you, I can't magnify it, but if you magnify that, you see it was 6mm perforations. And there's an auger inside there that carries the screenings up that pipe here and back into the sewer. So that's the heat pump associated with the with our Rowan. So our Rowan extracts about 3 degrees centigrade from the heat that flows into it, and then the heat pump will take that up to whatever temperature the building is designed and the building calls for. So Winterthur in Switzerland there, that was heating this building that you can see there, and on the right here is that's the screen that's just being dropped into the excavation that was made for the in the pump station there. So in this particular instance at Winterthur, there were the sewer flow 60 litres a second, and the flow that was through our heat exchange units was about 60 litres a second. The thermal power generated was 600 kilowatts, but most importantly there, the cooling water was the cooling effect was 480 kilowatts. So you tend to need cooling to make these make the projects economically viable. Right, so what I've got in the notes section of this that I can't read because of the way I'm presenting it is a little bit of detail about here. So if we go back here, so what the Winterthur building had was underfloor and wall heating. So it only required 37 degrees centigrade water in it. If you have underfloor heating, we typically heat water up to 45 to 47 degrees centigrade for the underfloor heating. And our understanding is that if you need radiators like you do in a lot of buildings in the UK, then that's 65 degrees. So in the same way that most air source and ground source heat pumps require a well insulated building, the same is true of here. If you're taking sewage up to 65 degrees C, it's probably not viable. If you're taking it up to a lower temperature, then it's got a fighting chance of helping you. Each particular application is individual. As you saw from that, you can imagine the sewer are equally variable from building to building. So that's the unit in its entirety, with the inlet here on the left hand side, the outlet there. So the screened sewage has still got particles in it, but they are smaller than 6 mil. They will fall out in this section here, and this auger here will convey them out of the will collect them at the bottom. There's a V-shape. It's a V-shaped bottom that will collect the particles in the bottom and take them out for sedimentary. Well, the sediment will be removed. So the trick of these units is that they are 100% stainless steel, so they are very, very corrosion resistant, and this is automatically cleaned. So you can see there it's a tubular heat exchanger. So the tubular heat, the water to be heated up flows through these tubes against the flow of the incoming sewage, which starts off at nominally 14 degrees centigrade and goes out at about 11. After a while, as you can imagine, these things are sitting in sewage. You get biofouling. That is the primary cause of a heat exchanger suffering from performance efficiencies in a sewage work, and it can actually reduce heat transfer efficiency by 60%. So what we have is an automated cleaning system to keep those tubes clean, to bring back the efficiency of the tubular heat exchanger. So that's just another depiction of the solids flowing, settling out and being carried out via the auger at the bottom. So this is highlighting the impact of wastewater on those exchangers. So the biofilm is made up of microorganisms which grow on the surface of anything immersed in sewage in no time at all. I can vouch for that, having spent half my life walking around sewage works. You get sedimented solids which are settled out and removed, and the effect is a negative impact on the heat transfer efficiency. So the mechanical cleaning element of our heat exchangers is critical to its success. So too is the stainless steel manufacturing, and there you can see the heat exchanger cleaning efficient. So you can see there where the tubular heat exchangers have been cleaned, and then where they haven't been cleaned. So it's quite clear, and you can go into one of these things after 5 years and they will still look like that. We recommend a service every 10 years, and that's one of the key benefits of this unit. It is, to all intents and purposes, it is nominally a fit and forget. You only need to service these once every 10 years, and it's not difficult service to undertake. So the difference between a tubular heat exchanger, as you can see there, is they're fairly easy to clean, and there's a lot of space around here for the sediment to fall out, and additionally there's a lot of space for the biofilm to grow, and it's very simple to keep clean. A more common form of heat exchanger, which has a far higher specific surface area, so you get far more heat exchanged, is a plate heat exchanger, and these are the sorts of things that you'll find in your boiler and all in other sorts of places. And you can see there convoluted parts of the plate to increase the surface area, and you can see they're all squeezed together here quite tightly. Well, if you put that into sewage, you really are asking for trouble. You get screenings blocking it up like this, and you get biofouling, which is much more difficult to clean, as you can imagine, than a straightforward tube where you just run a cleaning element down it and keep it clean. So that's the unique selling point of these, and that's why they are really only applicable for dirty water applications. If you've got the effluent off a sewage treatment plant, once it's all been through the process and it's been cleaned up, you probably want to go across to one of these plate heat exchangers. But then the temperature's lower, so you haven't got as much heat to extract. So that's the benefit of ours. You can stick it in underneath the building, take your low grade heat, stick it back in the building, and away you go. This is a nursing home again in Switzerland, and I think it might show you later where the application is, or it may not. But if you want, where's my cursor? It's under the asphalt here. And again, they use a buffering tank there, so it's a buffered operation to reduce the size of the unit and keep the flow through as smooth as possible. And particularly in a nursing home, you'll get all the laundry done at one particular time. So you want to buffer it so you capture all the laundry water, keep it there in a warm water tank, and then send it through our heat exchanger at the maximum rate that the heat exchanger can cope with. In this particular instance, it was 40 cubic meters a day, and the thermal power it generated was 50 kilowatts. So actually, going back to, if I just go back up here, I think I explained on this that we took the thermal. This had wall and underfloor heating, and that's how we get the heat out as well. So that's where the cooling benefit came in from Winterthur. That was really quite important. Going back here. So that's just a graphical representation of our heat exchanger unit there, and then the heat pump there taking the temperature back up so it could be used for heating within the nursing home. What they call a batch operation is actually a buffering operation. That's a German expression, the batch operation, but that's the buffering, that's the buffer tank there. The batch operation is the operation of the laundry and the way it comes back to the UK, back to the machine. Oh, there we are. I knew there was a slide in here somewhere. So that's your shaft in there going down to collect the sewer. So you can see it's quite unobtrusive. That's the equipment in the that's heat exchanger itself. Okay, so that's the end of the the nursing home. Now we're going to talk a little bit about the clinicum, which is that's a sterilisation washing equipment, which again is there's a storage buffer, but what they do there, they extract about 60 kilowatts of heat, and it's directly used to pre-warm the water that goes in order to wash the sterilisation tool. So that's very hot water coming back, taking the hot water out and putting it back in. And some industries, their water is so hot that it needs to be cooled down before it goes into the sewer, and this is one way of doing that, as well as extracting the useful heat. So that's the unit in the basement of the Munich hospital. I've actually been and seen that. I've touched it, and you wouldn't honestly know it was there. It just chugs away, and as you can see, it's nice and clean. It's all enclosed. That was quite awkward, so we had to break it into 3 pieces in order to get it into the access there. So that had to be brought down some stairs and in there. So this is just the flow diagram of what happens to the high temperature water. comes in, it may or may not be pumped in, but then depending on whether or not it's wastewater. So I don't know if the clinic needed a screen, but it's buffered in order to smooth the flow through the heat exchanger, and it's very low maintenance. So there are several applications for this where it has already been used in Germany and Switzerland and America. So it's used in public institutions, hotels, hospitals. That Lucabad there is a hot water spring thermal bath, so it extracts the heat from the hot water springs actually, and is used to heat the building in winter. And it's used in breweries and paper mills, textiles, food industry. All of these industries have potential for using their effluent as a source of hot water. Another potential application for the for extracting heat from sewers is if you've got a heat network. And this is a Department of Business and Energy. There are several hundred. In fact, I think there's about 1,500 heat networks in the UK. They tend to be fairly small and local, but in essence, they heat. I mean, I'm probably preaching to the converted, but they are networks to heat buildings rather than them having their own source of heat. And this is just one of the sources of heat that can be used to bump up the temperature of the water in the heat network. So this is a worldwide reference list of row winds that we've got throughout the world. It's actually quite old. There's another 10 that they've sold since then, but you can see there's Germany, France, Switzerland, USA, Canada, and also Poland and South Korea. But there are no Huber references for extracting heat from sewer in the UK. And why is that? Okay, so there's no government incentive. There's often a long payback, if any. You need underfloor heating, because if you need to heat it to 65 degrees C, then that's difficult. So you need a building, and one of the biggest hurdles is the diverse ownership of asset and who pays and who owns it. So the water company owns the sewer and the water company owns the sewerage. The landowner might own the land and the building, somebody else might own the building, and you might have the building occupants. So there's all sorts of interfaces to be handled. And to access the sewer, it may well be that you have to go down through a road. And some of these are accessed underneath the road. So whereas in Germany they've got and a lot of countries they've got municipalities, so you've just got one institution that you're dealing with. Over here it is very, very difficult. And combined with that, I call it a can't do attitude. The UK water industry is phenomenally reluctant to do anything different. And they are, so for example, even though we typically remove 3 degrees centigrade from a bleed off from a main sewer, it doesn't stop water companies worrying about the effect of the temperature on their sewage works, even though it is minimal. And I trained as a process engineer, and it frustrates the hell out of me that all sorts of problems are put in your way, including that one, which shouldn't exist, but does. There is, I believe, in the UK, a corporate inability to just have a go and do the right thing, certainly without government incentives. So that's just a whole raft of reasons why it's not. There are none in the UK. We are pursuing several options in the UK at the moment through a partner company, because if you think about what needs to be done, you've got a civil intervention to make. You've got to knit together all of the stakeholders, and there's just a few of them listed there. You've got to interface with the heat pump manufacturer, and then you've got to interface with the facilities of the building. And little old Huber, we just make heat exchangers. So we put together, and I'll come on to that later, and I'll give you the contact details. If any of you have got an opportunity to do this, we would welcome hearing that, but it wouldn't be us that you would be dealing with. It would be our partner organisation called Landmark Engineering, who have assembled a team that can answer, that can deal with all of the interface issues, including the civils interventions, the facilities interventions in the building, etc. The only place this has been done in the UK, as far as we're aware, and I think I'd like to think we would have heard about it if it'd been done anywhere else, is in Scotland. And the reason it could happen in Scotland is that Scotland are driving for the government, and the government is much more progressive and aggressive in its pursuit for low or zero carbon. And the water company is essentially a government-owned company called Scottish Water, and they have a commercial arm called Scottish Water Solutions, and they also have a commercial arm called Scottish Water Horizons, and those two organisations are capable of taking an initiative and tying all the pieces together. So they have done a couple of schemes up on government-owned buildings, so they reduced the number of interfaces very sensibly, but it did require incentives and tariffs, and I know for a fact that the tariffs have been removed now. So I don't think there's any more going to go ahead. And they used plate heat exchangers. And so far, I've not heard whether or not they've worked terribly well. My suspicion is that they haven't met their objectives, and the company that installed them for Scottish Water, I don't think is operating in the UK anymore. So it's a shame, because it would, I think, successful. What he was talking about, what was going on up there, I think it would have been more successful for the rest of us, countrywide, and it would have been a fight about what equipment you installed, whether or not you install equipment at all. So summarise, it's a proven and very simple technology. The interfaces, however, are not simple, and they are complex. You've got different asset owners, you've got civil interventions, you've got some construction tie-ins, both with the sewer and then with the and then with the building. And it depends on the existing heat arrangement that the building has. Cooling is as important as heating, as it helps justify the cost. Each project is very different, which is why I haven't shown you any paybacks or anything else, because they will be completely irrelevant to any given situation that we find in the UK. The packages are all bespoke and applicable to the needs of A, the client, and B, the physical situation of the opportunity that's presented to you. So advices on packages can be are available from our partner organisation, Landmark, and when I send you through here, I've just put in, for your interest, a link to a Canadian project write-up in a Toronto hospital that's under construction at the moment. So my final slide is the contact details for Landmark Environmental. So I'm happy to field questions about own technology, but in terms of putting solutions together, if you find anything, please feel free to contact either me, or if you've got this presentation, then contact Stephen at Landmark Environmental. Right, so I think that was about half an hour. Philip, have many questions been posted in the chat line?
Yeah, so yeah, thanks for that, Mike. Very informative, and yeah, hopefully another solution for us all to look at in what is a very difficult outlook for obviously the net zero carbon agenda in the UK and worldwide at the moment. So it's always good to have different options to look at, and as you say, it depends on the scheme and what you can and can't do, and what what suits really. So Mike, if you're able to just click on the comments box just at the top, you should be able to see.
I need to get to that point. Let me. Right. Okay.
Yes, if you just click the little speech bubble, just that's the one. Yeah. So you can see there, and Jess has put a few questions on. So if you want, maybe just. I think the first one's probably going to be difficult to answer, but the other ones might be able to give some feedback on.
Yeah, we'd have no way of costing that comparison. You'd have to come, if you want to understand how a costing might work, you need to come up with a scenario that we can cost, because there are so many variables. It is impossible to come up with a general reply to that. In which applications would your system be an attractive option to consider? Yes, you need a sewer. Yeah, good question. You've answered it there. You've answered your own question. So you do need a local sewer. You need that sewer to have enough flow in it so that you can take a bleed off it all the time without causing the water company any concerns about lowering the temperature of their sewage, even though I believe that's as a process engineer, I don't believe that's a valid concern. But you do need to address that concern. Yes, you need a building. That building also needs to have typically underfloor heating. These seams don't tend to stack up if you're trying to heat radiators. Yes, a district heating system. We have looked at that in the UK, but the district heating system hasn't gone anywhere. But there's one down in Bath. There's one that we are. There's a dialogue that springs up periodically and then goes down. But you've answered your own question. A building that's insulated, and Germany always say if you need to cool as well, that is another benefit, and that is more likely to go ahead, because the cost savings associated with cooling are significant, are higher quite often than heating. So yes, all of our systems are. No, that's not true. So the clinic doesn't use a heat pump, but the heat pump is required if you need it into it. So what it will do, it will take low grade heat at a low temperature of between 10 and 20 degrees C, and the heat pump will then take that up to your 37 degrees C in winter or your 45 degrees for underfloor heating. So yes, by and large, they are all coupled with a heat pump, but the coefficient of the COP is so big, if you need to get it up too high, that it doesn't work out as a viable option. And Landmark, our partner organisation have relationships with heat pump manufacturers so they can understand the implication, because it depends on what the building requires and the flow rate through the sewer in order to be able to design a system. But the system design will incorporate our heat exchanger and a heat pump. Yes, you're reversing the heat pump, and at Winterthur you're just using the same pipes that circulate hot water, take the cool water out. Right, that's it.
Yeah, no, thanks for that, Mike. And I just suppose would open for any other questions that anyone may have, whether they want to use the chat or whether they want to put the microphone on and maybe ask a question. Yeah, please do. I think we've got Mike for another 10 minutes or so. So yeah, please happily. I think there's another one just go on there actually, Mike.
Okay.
Sorry, an extra couple of ones on there.
You surrounded the wastewater network affect the efficiency? No, not really, because these well, in our case, we normally put these in so close to the source of the sewage that the temperature of the sewage is the overriding factor. I am going to ask because that question from Jess Tyndall does interest me, even though I can't answer it. So I'll see if I can find an answer. But I'm guessing it will be the same one I gave.
Yep, just actually there was one you just missed there, Mike, about someone was just asking what sort of controls are required with the BMS to interface to your system.
Controls. Okay, so these things are controlled by themselves. Our unit can come with a straight. Our unit itself is controlled with a local control panel. It will then need to interface with basically the building will call our heat exchanger for heat. So there'll be a call to run basically, and then it will run in order to develop the heat. The rest of the control system will be dictated by whatever is in the building and whatever the heating system is. If it's a building, it will be the building heating system, and that will need to be designed around whatever's in the building. Our heat exchanger is just simply run by a local control panel. If any fault detection on cleaner, etc. That is a good question. We do have monitoring. It would be detected by a fall off in efficiency. And we have a package of we can measure the influent and outfluent to make sure of that. So I can find more details out on that, but it will, in essence, it will be a tail off of efficiency, and that will be the core means. But I'll find out I'll get hold of an OAM manual and give you more. Shall I deal with you, Philip? Shall I send the responses back to you?
Yeah, if you could, yeah, and I can share that. It's no problem.
Yeah. Okay. So I'm just going to take a photo of some of these questions. Can't find my camera on my phone.
You should be able to have access to the items on the chat as well, Mike, after the call's finished,
Okay.
to get back to any questions as well. I think there's probably just one more there, just from Jess again. I think if we do that one, that probably covers all the questions, Mike. Just about the automatic clean system.
Yeah. How does the automatic clean system, does it wear away the heat exchanger every time? No, it doesn't really wear away the heat exchanger in any significant fashion. It's very simple. It slides along the stainless steel tube, and we suggest they're replaced at 10-year interval. That's how long they're designed for, and there's no significant wear during that period. So it just scrapes. It's like a ring that just scrapes along there. I've got one in the office.
No, excellent. No, Mike, thanks again for going through that. And like I say, I think it's an option for us all to maybe consider in the future, and may or may not be applicable to the schemes we're running at. But yeah, thanks again, and thank you everyone again for attending, and hopefully catch you at our next technical seminar.
I think if we can get one in the UK, it will take off. So if any of you can help us do that, that would be greatly appreciated. I think though, we're going to need some incentives, and I think we may find some coming. So if you've got a realistic application, start the conversation now, and perhaps wait for the incentives to crop up later.
Excellent. No, thanks for that, Mike.
Super.
Okay. Thank you very much. Thanks, everyone.
So I will try and find out about fault detection, and I'll try and find out about a 400 kilowatt borehole system.
Yeah. No, like I said, you can share that with me. I can share that out as well.
And I'll send the presentation through to you, Philip. That's great.
Yeah, that's great. Lovely.
Okay.
Excellent. Okay. Thank you, Mike.
Thank you. Bye, everyone.
Cheers. Night.
Thank
Bye.
you.
Bye. Pleasure.
Cheers. Cheers, Matt. Thanks a lot.